introduction, Mr. Chairman. My name is Masunishi. I came from Toshiba Corporation in Japan. Today, I would like to talk about MEMS accelerometer with high accuracy and wide dynamic range. I have 4 topics today. First of all, I would like to give you an overview of MEMS accelerometer market. Let me focus your attention to this table. This is a result of your research on changing in MEMS accelerometer revenue from 2021 to 2027. As you can see, defense and aerospace and industrial application high. Growth rate is high. Example application are shown on the right. So defense and aerospace and industrial application are promising. The left figure shows the relationship between application and performance of MEMS accelerometer. Horizontal axis represent bias instability. Vertical axis represent dynamic range. As you may know, MEMS accelerometer are now widely used in commercial consumer applications such as cell phone, game controller, and smartwatches. Right figures show the characteristic of displacement detecting accelerometer. Depending on initial electrode gap, there is trade-off between bias instability and dynamic range. So there is a trade-off in MEMS accelerometer application too. Also, so however, breaking this trade-off opens the market. Opens the market. So our target is high accuracy and wide dynamic range MEMS accelerometer in defense and aerospace industrial application. So just to wrap up, our goal is to achieve the accelerometer with high accuracy and wide dynamic range. So next, let's move on principle and design. Left figure shows the principle of operation of MEMS DRA. DRA is a differential resonant accelerometer. And the right figure shows the resonant frequency of 2 beams. Initial resonant frequency difference, delta F initial, is shown. When inertial force act on proof mass, tensile and compressive stress applied to beams. So resonant frequency change depending on scale factor. So this is the principle of acceleration detection. Resonant frequency also change with temperature. So MEMS DRA use differential detection to eliminate temperature dependence. So MEMS DRA is a resonant detecting accelerometer, and there is no trade-off between bias instability and dynamic range due to the displacement. However, one factor that determines the dynamic range is the effect of mode localization. Resonant frequency approach to each other. When resonant frequency too close to each other, mode localization occur. The left figure shows the model of 2 resonator coupled weak stiffness. 2 resonator interfere affecting resonant frequency and amplitude. Resonant frequency of mode localization with single side perturbation MLSP and differential perturbation MLDP are shown like shown the right. So this picture shows the change in resonant frequency due to resonant frequency change due to stiffness perturbation. Right figure show more MLSP, left figure show MLSP, and right figure show MLDP. As you can see, mode localization occur. When mode localization occur, the resonant frequency change become nonlinear. So this figure shows the result of simulation of MEMS DRA with etching error. Left figure shows the change resonant frequency of two beams. And horizontal axis represent applied acceleration, vertical axis represent frequency. And right figure shows the resonant mode shape. There are in plane resonant vibration mode of resonant beam 1 and resonant beam 2. As you can see, resonant frequency approach to each other, mode localization with differential perturbation MLDP occur. So initial resonant frequency difference delta F initial and dynamic range are shown the right figure. Furthermore, the problem is that mode localization cannot be avoided when delta F initial is small. Furthermore, in-plane vibration and out-plane vibration mode of proof mass, there are in-plane and out-plane vibration mode. So, in-plane vibration mode of proof mass, MLSP occur. So, in our previous work, we improved the capacitive sensitivity DCDY by adding T-shaped electrode at the point of maximum displacement of beams. Symmetric T-shaped electrode improved bias instability in Alan deviation. However, delta F initial is caused by etching error. So symmetric T-shaped electrode improved accuracy, but delta F initial is uncontrollable and small. Therefore, we propose a symmetric T-shaped electrode. Let me focus your attention on the figure on the left. In a symmetric T-shaped electrode, the mass was varied by adjusting number of holes. So resonant frequency can adjust without capacitive sensitivity DCDY not change. So the table on the right shows the comparison of the code of delta F initial. A symmetric T-shaped electrode control and widens delta F initial, but does not change DCDY. So let's move on experiment results. This is the result of Alan deviation. Horizontal axis represent average time, vertical axis represent Alan deviation. As you can see, Alan deviation was almost the same. So there is no difference in noise between symmetrical and asymmetrical. This figure shows the experiment result of resonant frequency and scale factor of two beams. Right figure and left figure and right figure show the difference of symmetrical and asymmetrical T-shaped electrodes. As you can see in asymmetrical T-shaped electrodes, initial resonant frequency difference delta F initial is able to increase. So let's introduce our demonstration of high G measurement. This slide shows the experiment setup of high G measurement. MEMS DRA module fixed on rotating table and applied high G of centrifugal force. Radius of rotation is 50 centimeters. Angular velocity increases 0 dps to 3000 dps. The left figure shows the experiment result of high G measurement with symmetrical T-shaped electrode, our previous work. As you can see, mode localization occurred. On the other hand, right figure shows the result of high G measurement with a symmetrical T-shaped electrode in this work. As you can see, no mode localization has occurred. The right figure in pop-up shows the correlation between measured acceleration and applied acceleration and measured acceleration. As you can see, linearity is obtained from minus 40G to plus 40G. So let's go through the key point. We found that when the delta F initial is small, the MLDP and MLSP occur and determine the dynamic range. We propose a method of increased delta F initial without affecting the DCTY by changing only the number of holes in the T-shaped electrode to make it asymmetric. We demonstrate that the dynamic range can be extended to plus minus 40G without adversely affecting the run deviation. Acknowledgement and thank you for your attention.